In this module, we will discuss the phenomena of physisorption and chemisorption. In the study of surface phenomena, one basic type of process is the attachment of a substance to the surface. This process is referred to as adsorption. The substance being adsorbed is called an adsorbate, while the surface to which a substance is attached is usually referred to as the substrate. We encounter two primary mechanisms by which substances attach to surfaces: physisorption and chemisorption. Their distinctions are based on the way substances interact at the molecular level with solid surfaces. Physisorption, short for physical adsorption, is an adsorption process where molecules adhere to a surface without significant perturbation of their electronic structure. This type of adsorption is characterized by the absence of electron transfer between the adsorbate and the substrate. The primary interaction mechanism driving physisorption is van der Waals forces. These forces are long-range but relatively weak. The adsorbate-substrate interaction energy in physisorption typically ranges from 1 to 20 kJ per mole, similar to the enthalpy of condensation. This relatively small interaction energy is not sufficient to cause bond breaking within the adsorbed molecule. As a result, a molecule undergoing physisorption retains its chemical identity, although it may experience some distortion of its chemical bonds due to the influence of the surface. A key feature of physisorption is its non-specific nature. This means that virtually any adsorbate can adhere to any substrate if van der Waals interactions are possible. In terms of substrates, all solid substances can participate in physisorption. As for adsorbates, all gases below their critical temperature can be adsorbed, with the molecules remaining largely intact during the process. Physisorption typically occurs at low temperatures and is a rapid process. It is highly reversible, meaning that the adsorbed molecules can easily desorb from the surface under suitable conditions. Furthermore, adsorbates can form multiple layers on the surface during the physisorption. Chemisorption, short for chemical adsorption, is a process where molecules attach to a surface through the formation of chemical bonds, typically covalent in nature. This process is distinct from physisorption in that it involves a significant alteration of the electronic structure of the adsorbate. In chemisorption, there is an electron transfer between the adsorbate and the substrate, leading to the creation of new chemical bonds. Chemisorption is a highly specific process, primarily dependent on the chemical identity and compatibility of the adsorbate and the substrate. Certain adsorbate-substrate pairs of substances may interact strongly, forming robust chemical bond, while others may not interact at all. This compatibility is influenced by several factors, including the surface structure of the substrate, the availability of reactive sites on the substrate, the electronic configuration of the adsorbate, and the potential for electron transfer between the adsorbate and the substrate. The adsorbate molecules involved in chemisorption actively search for sites on the substrate that maximize their binding. This specificity of adsorbate-substrate interaction distinguishes chemisorption from physisorption. The adsorbate-substrate interaction energy associated with chemisorption is significantly greater than that observed in physisorption, in the order of a few hundred kilojoule per mole. The difference is primarily due to the formation of chemical bonds between the adsorbate and the substrate. As a result of strong chemical bonds created during the chemisorption, it typically results in an irreversible binding between the adsorbate and the substrate. The distance between the surface and the closest atom of the adsorbate in chemisorption is typically shorter than in physisorption, reflecting the stronger interaction and bond formation. Chemisorption significantly changes the electronic structure of the adsorbates. Moreover, the intense interactions with the surface atoms can lead to the breaking of bonds within the chemisorpted molecule. This results in molecular fragments that remain bound to the surface, which can play a crucial role in the catalytical properties of solid surfaces. Unlike physisorption, due to the specific and strong chemical interactions between the adsorbate and the substrate, chemisorption typically results in the formation of a monolayer. The term monolayer refers to one atom or molecule thick layer of molecules or atoms adsorbed onto a surface. In the study of surface phenomena, both physisorption and chemisorption phenomena are described by a physical quantity called fractional coverage theta. Fractional coverage quantifies the extent to which adsorption sites of the surface are occupied by adsorbate molecules. It is defined as the ratio of the number of adsorption sites occupied to the total number of adsorption sites available on the surface. This concept is illustrated in this figure, where a surface with multiple adsorption sites is depicted. Reactant molecules, represented by blue spheres, can either remain in the gas phase or be adsorbed onto these sites. The fractional coverage, theta, is the fraction of these sites that are occupied by the adsorbate. Studies of adsorption involve measuring the coverage theta as a function of the pressure of the adsorbing gas at a constant temperature. This relationship between theta and pressure at a fixed temperature is known as an adsorption isotherm. These isotherms provide valuable insights into the nature of the adsorption process, whether it physisorption or chemisorption, and are crucial for understanding how different factors such as pressure and temperature influence the adsorption of substances on surfaces.